welcome everyone who's joining us live today, and also everyone who's watching the recording later. Thank you for joining us for this deep dive session. I hope everyone's enjoying the battery day so far. We have an excellent lineup of speakers, and a lot of insights coming our way. Today, our deep dive session is going to be about using telematics data to monitor the health, reliability, and safety of electric vehicles in the field. And we have amongst us today Dr. Remco van den Berg, who is the senior data scientist at Twice. I'll quickly introduce him and hand over the floor to him. I know you're all waiting to hear him speak as well, but we're extremely happy that he could join us today. So Ramco leads the development of machine learning algorithms and physics-informed statistical methods that provide actionable insights into the health, safety, and reliability of batteries in the mobility space. Prior to joining, Remco was a project coordinator and faculty scientist at the European Southern Observatory. He holds a PhD in astrophysics and 15 years of experience solving complex problems in a data driven way, which is quite interesting. So I'll hand over the floor to you, Ramco. Feel free to introduce yourself a bit or maybe just dive into the presentation.
Yeah, thank you very much for the nice introduction. Cool. So yeah, thanks everybody for joining this session. Very excited to dive deeply into these topics with you today. So my name is Remco van den Berg. I'm working at Twice. So maybe I'll just start with telling you a bit about what Twice is for those of you who have never heard of this. So Twice is providing a digital platform for battery analytics software. It's quite a young company, about 5 years old. We have a team of more than 100 people now working there. Our headquarters is in Germany, in Munich. That's also the place where we have a battery lab, where we get our own battery cycling data to support everything we do on in-life data. And we also have offices in Paris and Chicago. And here you have some logos of partners that we're working with that you may recognize. We also work with OEMs, with mobility operators and energy companies. And the kind of spaces we're working in are in battery development. Can you see my pointer actually?
Yes, I can see it.
Great, thank you. So we work in battery development, energy. So battery development is basically based on the cells that we cycle in the lab. So we really bring our battery expertise there in the game to support customers that do more pre-life work, also in the mobility space. We work on stationary storage systems where we provide insights related to safety, also preparing or using second life applications as energy storage systems. And yeah, as you may be aware, there are actually 3 deep dive sessions at the same time. One is focusing on supply chain data. So basically, in this category, there's a deep dive on stationary systems. And actually, I will be focusing more on mobility. So any battery that basically moves. And one figure that I find quite striking here, and I'd like to start with this, is this one, where we can see that this is really the time where things are happening rapidly. So right now we are still fractionally are at quite a small share of electric vehicles, like commercial vehicles, but we started the exponential ramp up, and in the coming decade, 2 decades, things are really changing rapidly. And basically everything that moves on the street is going to have a battery very soon. So this also means that this is a very exciting time for battery analytics, because even though the fraction is low, the total fraction of vehicles that are already electric, the total number is rather large. And there's a lot of data already from which we can learn, vehicles where we can bring insights to. And also this is a great time to learn and to be able to apply what we learn now to whatever is about to come. So just taking another step back, like this is a huge task. It's also a complex task. And of course, since this is a global transition, there's a lot at stake. And there's quite a difference between doing things right and even doing things a bit right. Like we really want to handle things well. And for this, I would really like to make a strong case in this talk that data that is coming from the batteries can really help us to do this right. So what kind of data are we talking about? We're talking about lithium-ion batteries. They need to be monitored constantly, like their voltages, their currents, their temperatures, for basic and safe operation. And the kind of things we want to do with those data are related to safety first, right? We really care about personal and property damage, so we want to avoid critical situations like thermal runaway at all costs. But also, we want to use electric vehicles to go from A to B in a reliable way. So that's another important point where we want to use the data for. And then we are interested in doing this as long as possible with our vehicles to have a TCO, total cost of ownership, that's as low as possible. So there are discussions about health, like lifetime extension, etc., that we can address with this data. Now, at this point, you may be, or some of you may be shuffling on their seat a little bit because, yes, there is a BMS, and the BMS is supposed to sort of handle these kind of topics. But the BMS can do things very well, so they have access to a lot of data, a lot of sensors. So giving you like an indication. So a big commercial vehicle has already typically more than 1,000 voltage sensors alone that are being tracked. On top of that, there are currents and temperatures, typically 100 or several hundred temperatures sensors spread out over the temperature pack to basically monitor each part of each module separately. And these sensor readouts are happening at a very high frequency. So looking over the lifetime, we're talking about trillions of sensor readings for a BMS of a typical large commercial vehicle. But there are a few things that the BMS is not very good at. So it works with the provided data so that it reads directly from these sensors. So they're unclean, they're uncalibrated, there are all kind of sensor problems. It also has limited computing power. Like everything has to happen on the spot in the bus or in the vehicle. It has limited storage power, so it can't really compare with what happened yesterday very well, or even the week or the month before. And it also can't compare with its brothers and sisters. So there may be very similar vehicles that are out there. It doesn't really know if what it's reading is normal or not, because it can't really compare to the norm. So a BMS is really a reactive machine. It's not going to be predictive at all. And then the question is, can we do something smart to actually predict what is going to happen in the near or not so near future? And that's where predictive battery analytics comes in. And so the thing is, we don't have access to trillions of data points. We have access to aggregate data, still of the form like voltage, current, and temperatures. And the typical sensors that we read in the cloud, that we get in the cloud and that we can fetch via an API, are the system terminal voltage, the terminal current, and then some cell-based measurements. So for instance, the min and the max cell voltage at any time, the min-max temperature sensor readout at any times. And sometimes there are some more data if you're lucky. Sometimes the cell positions corresponding to the min and the max sensor readouts are also reported that we can also use. But in principle, the amount of data is already aggregate compared to what is available to the BMS. But then the machinery starts, right? We can build a dedicated machine learning pipeline around this. We can actually clean the data. That is much more efficient than what a BMS can do. So we have to first understand the way the data is logged. We can see if there's any missing data. We can find sensor values that are clearly non-physical, so that the outliers. We can also calibrate sensors. For instance, we find that the current sensor is not well calibrated, or there's a current sensor drift. We can all calibrate this out. And there are all kind of weird things that we can read in the data, and it never gets boring really looking at different data sets. There are different things you read that we have to take into account. like some weird unphysical correlations between current voltage sensors that are really caused by the way these data are assembled. So this is a super important task, cleaning the data before going on to the next step. And then we can basically, based on the chemistry of the cell chemistry of the data that's input, we can push it through the pipeline and have physics informed models that tell us what's the state of the battery. So getting different battery insights, and those we feed back to partners or customers, either via our Twice UI or a widget that can be integrated into a partner or a customer platform, or they're available directly via API endpoints. Okay, so before I start talking about exactly the kind of insight we get from these data, I want to stress one thing very clearly, right? So these algorithms can tap into the full historical data, not just of that fleet, but of not just that vehicle, but of an entire fleet of similar vehicles. So that's extremely powerful. And the digital infrastructure that is set up is now ready and scalable to very large fleets of thousands of vehicles. So really looking ahead into what's coming in the coming years, coming decades, where we have this huge transformation, and we need to provide insights to massive, vast amount of vehicles. And then, since these services are available, other services can be built on top. All right, so let's talk about kind of insights. So I mentioned this already briefly. So we look into safety, reliability. That's the most important thing, making sure that vehicles work as you want them and as you need them in order to be safe. But then going a step further, looking into the health and what we can do to actually make the best and longest use of our vehicle. Okay, so let's start on the top here. So safety and reliability. I want to show you a little bit about how things look like in our product and what kind of insights we bring to customers regarding a vehicle. So first of all, it's about monitoring that the BMS is actually doing its job right. So BMS is following rules to safeguard the safety of a vehicle. And we need to make sure that this works well by basically looking over its shoulder to see that the algorithms work as they need to. Secondly, looking in the thermal behavior to see if there's anything suspicious in terms of cooling systems that may be failing or so. And then more on the electrochemical side, are there weak cells that we can identify? Are there strange resistances that we measure that are rapidly changing and potentially hint at a problem? And then just basically checking that, sorry, that the kind of sensors that we monitor are correct, so that there are no sensors falling out that may hint that we can actually monitor what's happening in parts of the system. Okay, so just stepping back a little bit and looking at the kind of incidents and the kind of use cases that we serve in this UI. So this is one that I would like to focus on. This is actually not vehicle data. This is energy storage data, but just it helps to get the point across. So say that you have a storage system where you have an inverter and different modules are basically doing the same thing in this storage system. So there's the same load expected. And then what you see here, I hope you can read this. There's the temperature on the y-axis and there's time on the x-axis. So basically, as time goes on, because these modules are subject to the same load, there's a high degree of correlation between the temperatures that you measure in different parts of the system. But here, at some point in time, one module or one string starts to behave odd. So it reports a very different temperature compared to all its brothers and sisters. And this is a kind of anomaly that we can detect. And it turned out that actually the cooling system had a problem there. And using these insights, they could find the origin of this and fix it. So I only show you here the data stream where the problem is. If I would show you the future, then this temperature eventually gets back on track with all its similar modules. That's one thing. It will work similarly in a vehicle, but then the tricky thing is, of course, vehicles will do very different things. So we need to model exactly what's happening to a vehicle and what kind of temperature response is expected. And then by modeling this, we will get similar insights and we will be able to track these kind of anomalies. They're just harder to visualize. Okay, the second use case, this is a very interesting one because at some point we were contacted by a partner where they found that their SOC signal, so the state of charge that's reported by the BMS, was very unreliable and showing jumps. So the SOC signal jumped by like 20 percentage points in 5 minutes or so. And that makes it very challenging for, say, a bus operator to plan any routes, or very stressful for a bus driver if you see that your SOC signal is unreliable while you have like 50 people behind you sitting in the bus, reliant on you on getting delivered to point B in time. So basically here is the way we track the SOC signal from the BMS compared to our model SOC signal. And most of the time, there's like maybe 1 or 2% off. And that's totally fine because there are always margins and rooms for error. So there's a safety buffer that's taken into account. But then suddenly this whole fleet, from one day to the other, showed this problem at the same time. So this is not a vehicle-specific problem. This actually turned out to be happening all over the fleet. And it turned out that this is related to a BMS software upgrade that caused the algorithms to fail. So using these insights, operators could get back to the OEM for a fix. And in the meantime, use the insights from Twice regarding the SOC algorithm to understand and build in the safety margin where needed. And then the last use case I wanted to talk about is this one. That is monitoring the way that cells are balanced in different vehicles, all of the same fleets. So here is a subset of 7 vehicles where we have this KPI, which actually was developed at Twice. That's one number that basically tells you how the balancing system works. And that's taking also like weak cells and underused cells into account. And here, again, as a function of time, you can see that values fluctuate. Actually, not each vehicle averages to the same relative value because vehicles are intrinsically different, even though their data sheet tells you that they're the same, the exact same type and creation, like production time. But as most of those signals stay and fluctuate around 1, there are 2 cases that really stand out here. Like one rapidly changing balance indicator, which shows you that there's a problem with the usage of the modules in the system, and another more subtle trend that can indicate that things are not being used in an optimal way with regards to like lifetime that's optimized, etc. So with these insights, we were able to get this back to the operator and basically reveal to them that their bus system were not operated optimally, and even that at this point actually the bus was taken out of operation for inspection. Okay, so those were some use cases. Just getting back again, how this is shown in our product more on a full like fleet overview level. So here are the types of incidents we show. So different vehicles, different messages, which sensor are the problem, when problems start, when they end, if they end. And then there are different levels of alerting. So we don't want to wake up fleet operators throughout the night with alerts, right? So some alerts are quite low level of severity and they're likely to go away. But then as according to preference of a user, it can be filtered on like critical or high severity alerts that are being shown. Use this zooming in here, and yeah, so this is basically to summarize the safety and reliability. So now we basically have a battery pack that is being operated in a secure way and in a reliable way. And now I think we can focus a bit on health and warranty, which is also a very interesting topic, and it also deals with a complex relationship between like an OEM and an operator or customer who yeah who that relationship basically is centered around warranty, like who is responsible when a vehicle breaks down like prematurely, given warranty claims, warranty breaches. So this is a very interesting topic, and it really has to be monitored well, this health, so that both OEMs and operators can trust a provider like Twice and the insights that we bring regarding the health. Okay, so how does this look like in our product? So this is the landing page for one bus, which has been operated for many years, almost 6 years of data shown here. And so what you see here is a warranty package. I will focus on this a bit later. But the main panel is showing the battery health. So this is the state of health of this bus, according to a strict definition, which is very important to set, and which I will also spend some time on later. And that definition is shown here. So that's the main panel, and then you can also look for a specific month at a breakdown of how the bus is actually used. So this is in calendar weeks, and you see the fraction of time that the bus, in this case the bus, was charging, was being used, so we call uptime, or was not doing anything, rest time. And of course, you want to minimize the amount of time that your bus is not doing anything, because these are expensive assets and you want to make the best use out of them, for instance, by charging slowly or by using it for something useful. And this is another figure that gives an idea of how the bus is used. This is showing how the bus is actually charged. So what is the DOD and the DOD distribution, the depth of discharge, and what's the mean SOC. So you basically see at what SOC was the bus plugged in, and at what SOC was the bus plugged out. And based on this figure, you can already plan some optimizations to basically optimize the SOC window to prolong the lifetime of a bus. And I will share a bit about this later. All right, so let's talk about this use case of warranty. So this panel breaks down in basically a promise. So the OEM promises that this vehicle will have at least this much energy or capacity available for a certain amount of time, or a certain amount of or number of kilometers driven, or number of battery cycles, under the condition that some rules are not breached. And then it is to us to basically track this health over time and to make sure that indeed those conditions were not breached. And what we show here again is the state of health as a function of time that we learn based on our models from real in-life data with no significant constraints on the usage, according to a precise SOH definition of what this SOH should represent. And then we promise that we can measure this state of health with better than 2% uncertainty. All right, so now the question is, okay, that sounds like a cool claim, but how can we actually beat this 2% mark? So a few things are super important for this. So I already mentioned how important it is to clean the data that we feed into our algorithms. Like, you'd have the best algorithm in the world, but if the data is not properly cleaned, calibrated, etc., then those algorithms are not going to give the right insights. That's clear. But another thing that's important is this SOH definition. So how how do you measure an SOH? Is it based on capacity, energy, resistance? Within which voltage limits do you measure this SOH? What kind of hysteresis states do you allow? What is the temperature, etc.? And then once everything is set, then we provide these insights. And then, so this is based on continuous driving data, in-life telematics data, but we also challenge our users to check that the insights we provide are actually correct. So there's a tool for this in our UI where you can basically click on time and say, okay, actually I've performed a checkup measurement to validate that what you're telling me, what the capacity or SOH is actually correct. And then there is a script that you follow, and that script basically is the definition of the state of health that we provide. So we ask for a slow charge and discharge rate that is quantified. The constant voltage phase has to have a very low absolute cutoff current that is specified. The battery temperature needs to be controlled. There's no recuperation allowed during discharge, and the two voltage limits have to be specified precisely. And this is exactly the definition that we follow in the SOH that we provide. Now, let me tell you a little bit what I mean by these two voltage limits, because that has a huge effect in the SOH that we measure. So we basically separate between a gross state of charge window and a net window. So the gross window is on cell level, for instance, for an NMC cell, 2.8 to 4.2 volt, and that is the entire cell that's in principle theoretically available, as indicated by a cell manufacturer. Then when you put them all in a pack, then the pack, when the pack manufacturer sets a limit and says, okay, this is actually what you are allowed to use for driving. That's set by the OEM, and that is typically quite a bit a smaller window. So that is in this case basically 3.47 to 4.70 volt, and that's what we call the net SoC window. And if you use the entire SoC scale of the bus, then you will operate basically between these two voltage limits. Now, the thing is that the shape of the OCV curve changes as batteries age. There's OCV aging, and this is a super important thing to take into account. And we're actually talking to some big OEMs that have algorithms that do not always take this into account. So that can lead, if you don't account for this effect, can lead to a dramatic bias in the SOH measurement. And just to illustrate that a bit with this figure, I show you here on the y-axis the state of health capacity. So this is an aged bus, it's well below 100%. And actually this system has run 2,000 cycles, so that's many years of operation. And on the x-axis is the start voltage of the window of interest, and the different colors are different end windows. So if you would cycle from 2.8 to 4.2 volt, you would measure an SOH of 70%. Now, buses are mostly commercial vehicles, but also personal vehicles. They are usually used in the upper SoC scale. So if you just interpret the data as you read them and you try to infer the state of health from those data, you typically get values that are much higher than what's available in the full window. So green is the available window. That's in this case 75%, and even then you're well higher than what you get in the gross window. So defining exactly the voltage limits within which we are talking about when we define a warranty, for instance, is super important to be able to check if warranty claims can be made. Okay, so again, if everything is taken into account, we have this 2% promise that's actually backed up by a big insurance company, Munich Re, which you may have heard of. And so using this as a solid foundation now, the measured capacity and SOH, we can build very exciting things on top. And then we are really talking about predictive analytics. So this is one example that we launched recently. So that is an aging prediction, where we basically build on top of the SOH insights that have been performed up to today and forecast when the bus will reach end of life. So this is schematic picture, but what's actually happening in the kitchen is we are running models that predict potential futures, but we do this in a completely bus and cell agnostic approach. So there's some data coming in. So in this case, this system has only performed 100 charging cycles in total. Then and we don't assume anything regarding the cells, then the future is very uncertain. But now I'm going to start this video, if that works. We have to stop this. I start a video, and then you see what happens as time goes by. The prediction actually becomes more and more precise, and we can make a better and better prediction of when this vehicle will reach end of life at 80% SOH. So these are the kind of insights we bring continuously. And yes, so we do this as I said, in a cell agnostic approach. We also provide another way of doing this. So we provide also hybrid models, which some customers are interested in. So then basically we use the existing database of what may happen to buses or vehicles as they age with the data as they come in, but combine it with a third pillar, which are lab measurements for the specific cell that is used to make the battery pack of the bus to get a announced prediction accuracy. Now, another thing I would like to show you is also a very interesting use case, which also builds up on this SOH and capacity estimate, and that is to look into potential lifetime extension. So basically, we find many fleets and many vehicles, mostly in the commercial sector, that have very predictable routes, and they may always cycle a small part of the battery, such as from 60 to 100% in SOC. Now, this is not usually the best range within which you can cycle a battery to prolong battery life. So basically, in this case, and this is a simulation, we could observe this cycling and make an intervention after 500 cycles and suggest a different cycling range from 40 to 80 instead. So since it's a super reliable, a super predictable route, it's very easy to accommodate. And there still is enough buffer in case you need a bit more capacity or energy to complete the route. Now, what happens, and again, this is in a cell agnostic way, this is from all the simulations that are built on lab data. We can predict what happens to these the aging curves if you change the way this bus is operated. And those are shown in the blue lines here. There are, in this case, 8 different models that were run based on our own lab data. And the blue line here is the mean, and the thin 8 lines, if you see them, those are the individual models. So this basically shows that you gain about 20%. You're likely to gain about 20% lifetime if you change the cycling of the vehicles this way. So these kind of insights we want to bring to our users, and we expect to do that in the coming months or so. So this is very exciting, especially if you have like a mind of sustainability and also the way to really reduce the cost of ownership of these kind of vehicles. And I'd like to really end with this quote, which I read in an article like a few months ago, which really struck me, that basically we are about as cost competitive as like diesel buses right now, and just expanding the lifetime by 10-20%, say, that will really be a game changer in making these e-buses win the race for cost competitiveness against like diesel engines. And then I think I've been speaking for about 35 minutes. I thank you again for your attention, and I'd like to close with this. This is a code you can scan if you want to have more information of what we're doing at Twice. You can also contact me on LinkedIn, and I'm happy to get you in touch with one of my colleagues. who can tell you more about these things if I can't answer your question. Thanks very much.
Thank you, Ramko, very much for this very insightful presentation. Really interesting topic. And yeah, I'm just going to open the chat now. If you have any questions or any comments from the audience, feel free to drop your questions in the comments if you want. I don't see any at the moment, but I think people just need a beat to think about this and really capture the essence of the topic. Amazing. I think we are right on time, and we can close this for now, unless Ramko, you have any last remarks on the topic or any other points you want to share.
Maybe so. One question I sometimes get, because it seems like uh, almost magic, right? Because the kind of insights we bring related to the state of health or capacity we get from normal daily operation, and this is completely different from having to bring your vehicle to like a workshop or garage where specific cycling tests are done, where you take a vehicle out of operation for maybe 48 hours. So this allows you to make longer and more continuous use of your battery assets. So if that point wasn't really clear yet, I'd like to stretch it one more time.
Amazing. Not pretty clear. We do have one question from Ramona. Um, are you using spectrometry impedance as a method of battery verification to ensure the accuracy and reliability of battery performance assessments? Do you have any comments to share?
Yeah. So thanks a lot for this question. So basically, the main way that we validate our procedures are the most are basically exactly what we promise to provide, right? We provide the the total capacity that you can charge in a battery system within 2 voltage limits. So this is really the kind of data that we use. Yes, we use other methods for our cells that we rotate in the lab, that we cycle in the lab. But for our insight that we bring to mobility customers, we don't require any interventions like this, which would require to take your bus out of operation.
Wonderful. I hope that answers your question, Ramona. And folks, if you have any other questions, feel free to drop them in the chat, or you can scan the QR code and reach out as well, reach out on LinkedIn as well. Great. With that, we can close the deep dive session for now. And a big thank you for everyone who's joining. I wish you a great rest of the day, watching Battery Day and taking on all the juicy content. But please tune in on the stage for the closing remarks for the Europe focused section. But before that, a huge thank you to you, Remco, for joining us and providing with such an insightful presentation. We are very happy and
Thanks a
glad
lot.
that you could join. Yeah,
Thanks a lot, everybody.
perfect. Thank you, everyone, for joining.
Bye
See you
bye.
later. Thank you.